Main topic is FCC, which is the center of any U.S. refinery. Not necessarily other refineries in the rest of the world. Some Oriental refineries don't have an FCC. They have a hydrocracker as their main cracking unit. So, but anyway, when you want gasoline, you almost have to have an FCC. Also get into alkylation after that, because that ties in with FCC. They're both gasoline units, and if there's time left, I'll get into cat reforming also. So let's see, it's going up to the beginning here. Okay. Okay, then don't pay any attention to that number there. That was another place, another time. But anyway, same course. Roughly what we'll go through: definitions, overview of the reaction section and fractionation, a little bit of the history of cat cracking. It's a pretty interesting history. And actually, we won't get into that. We'll get into some product yields and quality versus feed type, what kind of yields and products you get versus reactor temperature, and a little bit into mechanisms. You know, does this thing advance? Does this thing advance? Forget.
I think so.
I thought it did. I can do it with the...
Okay. Oh yeah, actually the mouse is probably better.
Yeah, okay. But anyway, that way I can just hold one thing. So let's see, how does that thing advance? Well, I'll do it with a mouse, I guess. Okay, definitions on fluid cat cracking.
Did you want to put that on full screen?
On what?
On full screen here? One of these modes?
Okay.
Yeah, okay.
All right, yeah, we'll read it a little better that way. Okay. Purpose of an FCC, it doesn't take any products that are saleable. It takes everything heavier than diesel, basically. And it's somewhat limited. It can't take the real bottom of the barrel, but it can take fairly heavy stuff. And so basically gas oils are the feed. They can come from the crude vacuum unit and sometimes from resid conversion units like cokers. And it cracks those gas oils to 430 and lighter, and with the aid of a fluidized silica alumina catalyst. Very fine catalyst, about like talcum powder. And okay, then reaction scheme. Hot oil mixes with hotter catalyst and regenerator. We'll see a picture of how these two units coordinate with each other. But anyway, a lot of the heat comes from catalyst that's hotter than the oil feed coming in. And then you flow upflow in a riser, a big line, probably 3 feet, 4 feet in diameter, to the reactor fluid bed. Most of the cracking actually goes on in the line going into the reactor. And in the old days, with the much less active catalyst, you needed the riser and the bed, and then a lot of the reaction went on in the bed. The reaction's so fast now that it goes on, and basically it's done by the time it reaches the reactor. So let's see. So then actually the reactor part helps to separate the products that you get from the cracking from the catalyst. And then the catalyst actually goes over to another vessel on a continuous basis, and with a slipstream into a fluidized combustion unit. The air is introduced, and you burn the coke off continuously. Typical operating conditions in a cat cracker are 10 to 30 psig. Temperatures in the reactor about 890 to 1,000. And the regenerator 1,100 to, that's probably more like 1,350. So like I say, the hot catalyst comes back here and helps heat up the feed. And what you're trying to convert to is 430 and lighter, basically gasoline and lighter. And and typically you'll get a conversion of 60 to 80 volume percent. So, okay, what do we got next here? All right, see now, is that the next one? I'll get back to the other.
Back arrows on the keyboard.
Oh, back arrow, okay. Not backspace, but
Back arrow.
say backspace or the?
Back key. There.
Your arrow keys.
Yeah, okay. I'm trying to get to the other screen. Okay, I see. Well, this is good. I can just do it this way. Okay, typical feeds and products, and a little bit about the catalyst. Now, API is a petroleum measurement of gravity, and that's probably about 0.9 specific gravity, 0.9 versus water. And endpoints typically 950 to 1100. And the feed typically comes from a crude vacuum unit. It's called LVGO, light vacuum gas oil. And so if you have a coker, if you have some a real heavy crude refinery, you'll have a coker, and the coker gas oils will come over there also. And the limits, how heavy can the cracker take? And there's some measurements, petroleum type measurements, that tell you how bad the feed can get before it causes too many problems. 0.1 and 0.4 Conradson carbon residue. That's a measurement in the lab that tells you basically how much heavy ends are in it. And the metal contaminants tend to foul the catalyst, 0.5 to 2 ppm. Nickel plus vanadium, most of the metals fall into those categories. Now they've developed a ResidCat cracker, and I've added this, but that you can go a lot heavier and a little more expensive unit with more regeneration involved. And there you could go all the way up to 7% CCR and 20 ppm, so you can handle a lot heavier crudes. But if you don't want to put a coker in, you sometimes go to an RCC. Okay, what products do you get? You get fuel gas. You get basically the whole slew, the whole spectrum of organic chemistry. And so anything from fuel gas, which is C1, C2, to propane, propylene, C3s, butane, butylene, C4s, gasoline. Then you get a diesel stream called light cycle oil, which is very bad diesel, not very good. And it's one of the products in the refinery that you have to figure out what to do with, how to get rid of it. And they also make some heavier streams. Usually these heavier ones are recycled to extinction. You don't take very much of that. So, okay, the catalyst is about a 60 micron average size. They're very small. And like talcum powder, as I said, silica alumina catalyst containing some zeolites in them. And basically how active the catalyst is how much zeolite you have in it. So bulk density, about 60% of that of water. Very high surface area. And it's mostly tiny little spheres and full of nooks and crannies and all kinds of internal surface area. This is where all the reactions go on. And which is pretty much true of most of your fixed bed catalysts also. They measure surface area in square meters per gram. Now, the typical consumption of this catalyst, you grind it up pretty good, because this catalyst is kind of a grinding powder. It's alumina, so it's about the same stuff you'd have on a grinding wheel. So very, very hard and abrasive. So you waste a lot of catalyst. Grinds up too fine to be and goes out the top. Say for a 60,000 barrel unit, 5 or 10 tons a day of catalyst you'll consume. So, and this could be an old number as far as what it costs, but annual cost can easily be $5 or $10 million a year just for catalyst replacement. So, okay, what do we got next here? Okay, here's a typical block flow diagram of the whole unit, including reactor regeneration and fractionation, and so let's see. We start here with fresh feed, LVGO, LCGO, vacuum unit or coker, and now sometimes you can hydrotreat this feed ahead of time. If it's really bad, you'll put a hydrotreater ahead of the cat cracker, and when you do, it'll operate a lot better. Here's the reactor here. So you can do this or not do it, but anyway, go to the reactor. Now this is fluidized. This is this riser we're talking about, and the reaction goes on there. And you mix it here with, sometimes you'll recycle back the heavy ends. And let's see, where's it? Yeah, and so here, there's catalyst coming in here too that mixes with the feed, goes into the reactor. And this, so what did we say, about 950, 1,000 degrees in here, boiling, a boiling mixture. And then the products go out here. Now the catalyst is continually having coke deposited on it, so it wouldn't last very long unless you regenerated it. So you continuously take a slipstream off of here and go over here where you inject air and burn off the coke. And like I say, this runs somewhere around 1100 to 1350 degrees F. And so you have a big blower here. In fact, we're putting in a blower now at Chevron El Segundo, 20,000 horsepower blower. So that's how big these things are. And so anyway, you burn it all off continuously, and then after it's burned off, it comes back here and mixes again with the feed. So, and it's hotter than the feed, so a lot of the heat's required. This is an endothermic reaction, so the heat's required, and so a lot of the heat comes from this combustion here, basically. And you're actually recovering the heat you generate by burning coke, and so that's useful back here. So now out here you have a flue gas, and a lot of times this is a huge flow. For instance, at Chevron, it's about 160,000 SCFM, and with a big unit, a lot of people put a power recovery unit in here. It's only like 25 or 30 pounds, but there's a huge volume. So you put a recovery turbine in here and make electricity. The Arco refinery, which is now BP in this area, has a power recovery unit on theirs that puts out 50 megawatts. I mean, that's a huge amount of electricity. But they recover that much, and it supplies over half the needs in the refinery with their power recovery unit. Chevron was thinking of putting one in, but we're not sure they're going to yet. But so a nice energy recovery scheme. Now coming out here, of course, you've got CO2. You burn coke, and you got some water. You also got some carbon monoxide, which is definitely toxic, and nitrogen oxides and sulfur oxides. So you got a big pollution problem coming out here. This is strongly regulated as far as what you're allowed to emit here. And this is coming out of here about 1300, 1350, so you recover a lot of heat. You usually have what they call it a CO boiler, or a waste heat boiler, so you'll recover a lot of the heat and make a lot of steam. And a lot of this catalyst that ground up, it's coming out here too, so you'll have to have, a lot of times you'll have an electrostatic precipitator or a bag house, or you have cyclones in the reactor, and we'll show that when we get to some detail there. Cyclones to remove some of the solids. Let's continue on with the product stream that you developed here in the reactor. It's about 950 and goes out here into the main fractionator, a very large fractionation column. It does very rough cut. It takes out a little naphtha stream here in the main column, and then this LCO, light cycle oil, which is a diesel stream. And you'd like to destroy all that and make gasoline out of it, but you can never get rid of it all. So let's see what else. Now at the bottom comes a lot of stuff that you might feed to the coker, and there's actually some limited uses for this decan oil. It's actually used to make bowling balls. I think the bowling ball people use it, but such a small amount, it's no big deal. And sometimes there'd be carbon black feedstock. Carbon black is one of the main black pigments for everything you see has black in it, probably has carbon black in it. Tires have a lot of carbon black. Sometimes you can use this to go to a carbon black plant. But in general, it's just a real dog to get rid of, and you just keep spinning it around and destroy it completely. Now here's where the fun part starts, where all the goodies are. All the goodies are overhead from this main fractionator. And don't show detail here, but like most fractionators, there's an overhead accumulator and a condenser. And and actually, now you compress it. There's a compressor here too. So you come out of here about 20 pounds, and you'll compress it up to about 200 or something like that. Then it goes through a fractionation train. Deethanizer to remove ethane and lighter, which becomes fuel gas. And it's got plenty of H2S, so you have to scrub out that H2S with an amine scrubber. Then that goes to the sulfur plant. Okay, now once you get rid of the fuel gas, now you go to a debutanizer, and now you have most of your gasoline coming off here, and that's the main purpose of the whole unit, is to make gasoline. So you had a little heavier gasoline coming off here, but the lighter stuff went overhead and condensed, and so this is a lighter gasoline, and this is the heavier here. So you remove the light ends from the gasoline. That's usually called a stabilizer. A lot of times when you say you stabilize the gasoline, that means you removed all the butane from it, because you wouldn't be allowed to have that in your gas tank or in the storage tank. Those would all boil off in the atmosphere. So now we got butane and lighter, C4, C3, C2, and you split the C3 and the C4 in the propanizer. There, propane, C3s go out the top, C4s out the bottom. Now, we mentioned last time, I don't know if everybody was here last time, but and if we have questions on it, we can pull out some other old drawings to explain this, but this is a cracking unit which does not add hydrogen like the hydrocracker I showed you last time. So it makes unsaturated compounds, because there's not enough hydrogen. As you break it down into the smaller molecules, they need more hydrogen. You're not adding it, so you make unsaturates. In the case of C4s, it's butylenes. In the case of C3s, it's propylene. So these have a lot more value. Those are olefins, called olefins. They have a lot more value than the paraffin, which is butane and propane. And the main use of them, now petrochemically they have a lot of use. Polybutylene's a plastic, polypropylene's a plastic. Even here, this makes some ethylene. Polyethylene can be recovered also. But anyway, these olefins are worth a lot more than the paraffins. And what they do in a refinery is they go to an alky plant and combine them with isobutane and make more gasoline. So that's another valuable thing this unit does. It makes gasoline, and it makes olefins, which go to another unit and make more gasoline. So, okay, and now all these products have sulfur in them, so you have to remove the sulfur from all of them. For instance, on the gasoline, they have a Mirox unit, and on the C4s, you have a Mirox unit also, which is just caustic scrubbing. Caustic reacts with H2S. H2S is the main sulfur form. It came in the feed here as complicated organic compounds with sulfur in them, and the reactor broke them all up, and most of the sulfur became H2S. So now it's in a vapor form, and you can do something with it. You can get rid of it in the sulfur plant and react it to elemental sulfur. So anyway, everything has to be desulfurized, and caustic is one way, amine scrubbing is another way. There's a lot of SOx coming out here, and probably Chevron's going to have to do something about that too on the project we're on there. So as I mentioned in the first session, basically what you're doing in a refinery is cracking the crude down to diesel and lighter, removing sulfur, rejecting carbon. That's the basic things you're doing, and a lot of these little processes are removing sulfur. And okay, any questions on the overall scheme in a cat cracker? All right, we'll get to a little history on it. Cat cracking. When they first started processing crude oil, all they wanted was kerosene for lamps and stuff like that, and fuel oil for boats, you know, and heavy fuel oil. Gasoline, it was so volatile, they didn't like it. They just dumped it back in the ocean. So we can't quite get away with that now. And that's what they used to do. They used to dump the gasoline. They didn't like it. It smelled bad, and it was too light to use in a lantern. But we've come a ways since then. And then finally, this guy here from Gulf, who's long gone, developed a catalyst that was able to crack crude oil. And then the next guy came along, Houdry, and he came up with a little better catalyst. And actually then he put it in a fixed bed, just like we saw in hydrotreaters, just a reactor with filled full of catalyst particles, not moving, not fluidized. But that coked up so fast that they had to regenerate the catalyst every 10 minutes. Well, that's a little not real economical. Shutting down getting a 10-minute run and shutting down the unit to regenerate every 10 minutes. So finally, Saucony Vacuum, which is Mobil, which is now ExxonMobil, they came up with a thermophore cat cracker process. This, instead of shutting the unit down, they would physically take the catalyst out in buckets and transport it over somewhere and burn it off and then bring it back. Kind of crude. They didn't know anything about fluidization then, so they actually physically transported the catalyst, in buckets. So kind of crude, but still it was a lot better than a 10-minute cycle. And finally, the big breakthrough, Standard of New Jersey, Exxon. Esso then, and now Exxon. But they discovered that you could get a very fine solid particles and actually pneumatically transport them. They were very, very small particles, so you could lift the particles with a gas stream or air stream. And basically they invented the whole concept of fluid beds. I mean, whether they invented it, who knows? I don't know if it was used in anything else before that. But anyway, that was the first time that the idea was thought to be used in cat cracking. And what spurred the real invention, which is about what spurs 80% of the inventions, is war. I don't know if you ever see History Channel, but they have statistics on there, and 2/3 of the things have been invented in wartime because of one side wanted to beat the other one, and they had some incentives. So this was another case, World War II. U.S. government combined with all the oil companies, Exxon, Amoco, and Kellogg down in Houston, and Shell, Texaco, EOP, and some companies that don't exist anymore, and said, we don't have time for each of you to develop your own process. Let's all put our brains together and see if we can get a process to make more gasoline for all our war machines. So that's really what was the incentive, and they did a pretty quick job. Within about 3 years, they came up with a fluid bed catalyst and a reactor type, and it was a little different then, a little cruder than now. It's come a long way, but nevertheless, it was better than 10-minute cycles. And so then, the Model 1 and the Model 2, and kept making improvements, and then 3 and 4. And actually, there's a lot of Model 4s still around. And then they made more improvements gradually. with these Model 1 through 4s, they were two separate vessels, the reactor and regenerator. Most cat crackers still are separate, but some companies came up with a single stacked reactor with one of them on top of the other, and I don't remember which. And the catalyst kept getting better. Finally, zeolites were a big breakthrough by the catalyst researchers. And that's a synthetic. Well, they're natural zeolites, and then they learned to make synthetic zeolites. Molecular sieves are actually zeolites. And much higher activity. This is where you went from reacting in the bed to reacting in the line going to the bed. And let's see if I get a picture of, okay, here, now we get a picture of how it works. These are pressure balanced. There's no pumps or no anything like that. I mean, there is a air blower blowing in here, but it doesn't supply any pressure for this circulation here. You got this gas oil feed coming in, and there's where the reaction goes on in the riser. And meanwhile, this hot catalyst is coming in with it and giving a lot of the heat necessary to make the reaction happen. And there's going to be a lot of stripping steam injection also. So this is flowing all the time, and then a portion of the catalyst comes out and gets regenerated in the regenerator continuously. Now, in the top of both of these, you're grinding up the catalyst continuously, so you have cyclones. Before the vapor can get out, it has to go through cyclones. And I don't know if you know how they work, but they're just a tangential tangential cavity in which you come in the side and you spin around the top of it, and of course the solids, are being heavier than the liquid, tend to hit the side wall and then drop. So it's a way of removing solids out of a vapor. And then you have two stages of it. So the vapor will go in one of these, spin around, solids go down, then even that goes through another one, a second stage cyclone. Same thing happens. And there's even further stages of solids removal beyond those. So both reactor and regenerator have two stages of cyclones. And this particular one is 8 pounds and 10 pounds. So one has to be higher than the other to keep the circulation going. And you control the flow of the catalyst and the oil with slide valves. It's marked as a valve, but really it is a big flat iron plate, probably 3 or 4 feet in diameter, sliding back and forth, hydraulically actuated, and it'll partially open and close and control the flow of catalyst this way and oil that way. So that's let's see, what else can we say about it. Basically, the pressure differential between these two is controlled, and you'll control the level. There's a bubbling level in here. This is coming up, and the solids and the liquid are boiling around like this, and there'll be a level here, and you'll control the level of catalyst and interface. And same thing in both vessels here. You'll have a level control, and you'll keep a certain level. And let's see. Okay, as I mentioned, the vapor that goes out the regenerator where you burned all the coke, that goes to pollution control devices, and this, of course, goes to fractionation. Yeah.
So what is the reason that reaction has to take place in the riser?
Well, okay, the reason the catalysts have gotten so active. It used to be the reaction went on in here because the reaction was so slow that, it started in the line, but then it finished here. Well, then the catalyst got so much more active, probably a factor of 10 or more. I mean, that much more active. And so finally all the reaction was done by the time it got here. In fact, what you wanted to do was stop it from going any further. So then you go in here, and a lot of times they'd have steam injection to cool it down then so it wouldn't overreact and start making coke. So anyway, that's they call it riser cracking, and so it's just a function of how do I get back to this? Okay. To the smaller version. I want to end show. Hit escape. On the keyboard. Okay. So I have some notes down here. Okay, yeah. I knew there was another slide I wanted to go to, so let's see here. I don't think there was any more up here. Yeah. Give you an example, since you brought that up, Eileen. There's another slide here which will show how the conversion has improved with time. Let's see, now that'll be over here, I guess.